Section 3.3 is about solving linear inequalities. We're going to talk about what an inequality is. Just like we had rules for solving equations, we have rules for solving inequalities. They're very, 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 very similar with one very important difference. It's when we multiply or divide by a negative. And then we're also going to talk about how to graph the solutions on a number line like we see here. All right, so what is an inequality? Let's start there. An inequality is a statement that one quantity is less than or greater than another quantity, okay? So instead of having equal signs, we're gonna have greater than, less than, or greater than or equal to, less than or equal to symbols. And we wanna solve or find all of the x values that satisfy the inequality, okay? An example of this is given, the inequality x is less than 2, which is written here. Where's my highlighter? Boom. So an inequality is a statement that one quantity is greater than or less than another value. And a good example of what an inequality would look like, it's a very simple one. It's something like x is less than 2. A solution to an inequality would be the set of all x values that satisfy this. So our solution isn't just going to be one number in this case, it's going to be an interval of numbers. Every single number or every single x value that is less than 2, okay? We can show this on the graph, which is given in figure 1. Notice that this graph starts at -2 with an open circle over it. We're going to talk about the open circle. And then we have an arrow going to the left that shades in everything less than -2. So this graph is showing that all of the values on the number line to the left of -2 is a solution to the inequality. Notice that there is, like I said, an open circle over the 2. That open circle indicates that the 2 is not included in the solution, but everything to the left of it is. If the 2 was included in the solution, we'll put a closed circle, and we'll see problems like that later. Okay, we're going to practice, this is a pretty straightforward inequality. We're going to take more complicated inequalities and try to solve and find the solution set for it. And then we're going to practice writing the solution in interval notation and also graphing. Okay, for the example that's done here, the inequality is x is less than 2. The graph is given here in figure 1. How would we write this in interval notation? In interval notation, this would be written as -infinity to 2 with parentheses around them, okay? In the next table, we have a few different examples of what inequalities can look like. We have greater than sign, greater than or equal to, less than sign, less than or equal to. And then you see pictures that explain what the differences in the graphs would be. Notice where we have open circles and closed circles, and then how you write this in interval notation. Notice where we have parentheses versus brackets. Okay, so let's start with the first one. X is greater than 3. Okay. Actually, let's take it back a step. This one is a greater than symbol. And this one is a less than symbol. Okay, so the first one here says x is greater than 3. That means that we want all of the numbers that are bigger than 3. If we wanted to graph this on a number line, you start your number line at 3, but 3 isn't included because 3 isn't bigger than itself. So we put an open circle around 3 and then shade in everything to the right of it because everything to the right of 3 is bigger than 3. Okay, in interval notation, this is saying we want everything from 3 all the way up to infinity. We never stop. But again, the 3 is not included. So we put a parentheses around the 3 and the infinity when we write it in interval notation. All right. Notice the subtle difference between x is greater than 3 and then the one under it. X is greater than or equal to 3. When we have that extra little or equal to line, that means that we are including our endpoint. That means that 3 is also included in the solution. How does that change our graph? If your endpoint is included in the solution, you put a closed circle around it. So notice that's over the 3, the circle is shaded in black. And then for the inequality, for the interval notation, when the endpoint of your interval is included, you put a bracket around it instead of a parentheses. Okay. And then we have another example, or 2 more examples with less than. X is less than 2, we just saw above. For x is less than or equal to 2, the only difference is we're including the 2 now. So we fill in the circle above the 2, and we put a bracket around the 2. One other very important thing I want to talk about with the interval notation, your negative infinity and infinity always has a parentheses around it. Always, 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 for negative infinity and infinity. For the other side of the inequality, it depends on whether or not that endpoint is included or not. All right, so now that we see like what this is what your final answer will look like for the inequalities that we solve. X is greater than 3, X is less than or equal to 5, X is greater than or equal to 1/2. That's what our final answers will look like. And then we have to show what that looks like on the graph and an interval notation. All right, now that we have an idea of what we'll be doing, let's jump into some, well, properties of inequalities. Let's go there, or solving inequalities. This box here is just showing us what an inequality might look like. So your linear inequalities are going to start off as a line. So ax plus b is less than or equal to, greater than or equal to, less than or greater than some number, or maybe another line, okay? So you'll have either 2 lines or a line and a number and an inequality in between them. You want to simplify the inequality or solve the inequality so that you have x on one side and a number on the other side of your inequality symbol. Kind of very similar to solving an equation where we wanted x on one side and a number on the other side of the equal sign, but now we have an inequality symbol instead. Okay, we're going to practice solving these inequalities algebraically. And we have properties of inequalities, just like we have properties of equality. Remember, we said we can add or subtract a number on both sides of the equation. Same is true for an inequality. We can multiply the same number on both sides of the equation. Same is true for an inequality. The only time we have to be very, very careful, or the 2 times I'll say we have to be very careful, if we are multiplying or dividing by a negative number, it changes the direction of the inequality. Okay, so that's what 3 and 4 are saying. If we multiply by a number that is greater than 0, then our inequality stays the same way. That's fine. But for number 4, if you multiply by a number that is less than 0, notice we started off with A is less than B, and then we're multiplying by a term C that is less than 0, so a negative number. And then our inequality changes directions. So we started off with a less than symbol, we end up with a greater than symbol. So I'm going to write it here in words. When we multiply or divide by a negative number, the inequality changes directions. So if you had a less than sign, it becomes a greater than sign. If you had a greater than sign, it becomes a less than sign. That's the only thing that's different than solving an equation. Otherwise, the steps will pretty much be exactly the same. Just pay attention to when you multiply by a negative or divide by a negative, switch the direction of the inequality. All right. Also, this table and the problems that we're looking at, they come directly from your book. We're on page, what page are we on? It says page 1 because it's broken down just by this chapter, but this is in section 3.3. All right, let's jump to some practice problems. There are a couple problems that are already done for us. I don't really want to do those because they're already done for us. I'd rather jump into our own practice without looking at the solutions. So we're going to start off with problem A. I'm going to write the work for this above. Problem A says we have the inequality 2x minus 3 is less than 6 minus x. Two x minus 3 is less than 6 minus x. The way that you go about solving this inequality Again, almost exactly the same as what you would do for solving an equation. We want to get all of the x's on one side, get all of the constants on the other side. So I'm going to start this one by taking the x that's on the right-hand side and adding it to move it to the left-hand side, okay? So if we add an x to both sides, this becomes 3x minus 3 is less than 6. So far, so good, right? Then next, we need to move all of the constants to one side. So I'm going to take that subtraction of 3 and add 3 to both sides. Then we end up with 3x is less than 9. And then we're almost done. To get the final answer here, we're going to divide both sides by 3. That's a positive number, so we don't have to change anything. We divide both sides by 3. We get x is less than 3 as our solution. All right, so that is the interval, the inequality that gives us our solution. The solution, I'm sorry, let me take a step back. What does this mean? This means if we pick any number that's less than 3 and plug it into that original inequality, we'll get an inequality that's true. All right, so we've solved this. We were also asked to graph our solution and write the answer in interval notation as well. So how do we graph x is less than 3? On a number line, we want to, I don't know, if that's 0, then 1, 2, 3, there's 3. We want to start off with a number line, identify where the 3 is. Is the 3 included in our solution? You always want to ask yourself that first. And the answer is no, because we only have a less than symbol, not a less than or equal to symbol. So 3 is not included in the solution. That means that we put an open circle around the 3. And then if we want to have all of the x values less than that, we're going to shade in everything to the left. So our solution would look like this, or the graph of our solution would look like this. Start at the 3, open circle, shade in everything to the left of it. Last part of our solution, we want to write this in interval notation. So for shading in everything to the left, that means every negative number as far as you can go is included in the solution. So that goes down to negative infinity. So we're going from negative infinity. We always put parentheses around infinity and negative infinity. And then we're going all the way up to 3. And the 3 is not included, so we'll put a parentheses around it. That's our interval notation. So those are the 3 things, or these are the 3 things that we should have in our solution. 1, when you solve, you should have x is greater than or less than or greater than or equal to or less than or equal to something. 2, you should have your graph where you shade in the solution area. And then 3, you should be able to write this in interval notation. And again, what does this mean? It means literally if we pick any number less than 3, when we plug it into the original inequality, 2x minus 3 is less than 6 minus x, we'll get a true statement. The number on the left will be smaller than the number on the right. Then let's do part B. For part B, actually, y'all are gonna kill me. I'm gonna move this, but that's okay. I won't move it. I'll leave it where it is. For part B, let's do a different color. We have 6 times x plus 2 plus 30 is less than 90. I'm gonna zoom in a little bit here. All right, 6 times x plus 2 plus 30 is less than 90. Just like previously with equations, on that left-hand side, we have some parentheses, and then we can combine some terms. We want to do that before we use the properties of inequality. So if we distribute here, we get 6x plus 12 plus 30 is less than 90. And then on the left-hand side, we can combine those terms. This would be 6x plus 42 is less than 90. And then we have to subtract 42 from both sides. 90 minus 42 would be 48. Yeah. So if we subtract 42 from both sides, we get 6x is less than 48. And just to be thorough, make sure everybody can see what we're doing here. Subtracting 42 from both sides. All right, and then last step, oh, I could have kept this. We want to divide both sides by 6. So our final answer comes to x is less than 48 divided by 6 is 8. So that's our solution. If we pick any x value less than 8, it'll satisfy our original inequality, which means that the number on the left is going to be less than 90 for any number that's less than 8. And then we want to write this or draw a graph for this. Again, on your graph, you really just need to put the, so I'm going to say that 0, boom. Here's 8. Put the number that you're starting with. We want an open circle around our 8. Again, because we have a less than sign, not less than or equal to. And then again, our answer is everything less than 8. So we'll shade in everything to the left of 8. And in interval notation, this means we're starting at negative infinity and going all the way up to 8, but 8 is not included in the solution. Then C, look at it. I think I might love C. I'm gonna need a little bit more space for C. So I'm gonna make a little more space at the top. All right, for C, let's put it in my favorite color. Oh, what did I do, y'all? Sorry, I broke it. All right, so for C, we'll start here. The problem was 3x over 4 minus 1/8 is greater than or equal to x over 2 minus 1. 3x over 4 minus 1/8 is greater than or equal to x over 2 minus 1. Let me double check that. Make sure I didn't make any typos. All right, so from here, just like we did when we had equations that include fractions, we can clear the fractions by multiplying everything by the LCD here, okay? So if we multiply both sides of this equation, or I'm sorry, inequality by 8, that will help us clear our fractions. So we have 8 times 3x over 4 minus 8 times 1/8 is greater than or equal to 8 times x over 2 minus 8 times 1. What does this give us? 8 times 3x divided by 4, that's 24x over 4, which is 6x, minus the 8's cancel out in the next term, so we have 1, is greater than or equal to 4x minus 8. Our life feels better already now that all of those fractions are gone. Take your time at that step to make sure that you are simplifying properly. But if you find the right LCD and you simplify properly, all of the denominators should cancel out. All right, let me double check, make sure I simplify it properly. Yes, 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 I believe me. All right, on to the next step. We need all of the x's on one side and all of the constants on the other side. So you can do this in 2 steps or 1. We can subtract the 4x's and then we can also add the 1. That's 2 different steps. We're doing it at one time. You can do it either way, both at the same time or do them separately. All right, let's try to do them at the same time here. So 6x minus 4x leaves us with 2x. The 1's cancel out on the left-hand side. So we have 2x's greater than or equal to. The 4x's go away. And negative 8 plus 1 gives us negative 7. All right, so 2x is greater than negative 7. Our final answer here is found by dividing both sides by 2. All right, so we have x is greater than or equal to negative 7/2. If you want to write that as negative 3.5, you can do that as well. Either way works, as long as your decimal is a terminating decimal, it's not repeating or anything, then you can write in decimal or fraction form. All right, this time we have a greater than or equal to sign, and we're starting off at a negative number. Let's think about what our number line would look like here, or our graph of the solution. All right, so if that's 0, 1, 2, 3, 4, negative 3.5, or 7/2. Let me write in some more stuff. Negative 1, negative 2, negative 3, negative 4. Negative 3.5 would be about here. Okay. Now, we have a greater than or equal to sign here. So instead of writing an open circle, that means at the endpoint, negative 3/5 is going to be included in the solution. So we want a closed circle there. And then this is saying x is greater than this number. So that means we're shading in everything to the right. And this is what the graph would look like. And then for the inequality, we want things bigger than negative 3.5. So we're starting at negative 3.5 and going all the way up to infinity. There's always a parentheses around infinity. And then for the negative 3.5, since it's included in the solution, we have an or equal to symbol there. We want to put a bracket around the negative 3.5. So let's move on to our next example, which is solving, those are solving inequalities algebraically. We also need to know how to solve them numerically. Remember, in this class, we talk about 4 different types of solutions. Well, we look at word problems, we look at algebraic solutions, numerical solutions, we look at graphical solutions. Numerically means with a table. So if we have an inequality like 4x plus 3 is less than or equal to 3x plus 5, you can put these, the left-hand side as one equation into your calculator and the right-hand side as another equation into your calculator, and then we'll form a table. Okay, so we let the left-hand side equal y1 and let the right-hand side equal y2. Put those lines in, and then we're going to look at the table associated with these 2 linear functions. All right, in your graphing calculator, this is what it would look like to type the answers in. Ooh, what happened here? You can see what the graphs would look like right there. But to solve numerically, we want to look at the table. Okay, so we can see for each x value what the different y values would be. And then let's compare to see which one's bigger. When x is -2, y1 is smaller. Then for the next line, so y1 is smaller, -5 is less. What is happening here? Is less than -1. And then we have -1 and 2 for the outputs. Y1 is less than -2. And then we have 3, 5, still less than, 7, 8, still less than. When x is equal to 2, y1 and y2 are equal to each other. And then after that, y1 is bigger than y2. We can just look at what's happening here and see that. So what's this telling us? And we can match this up with the graph too. At this point where x is equal to 2, so this is x equals 2, x1 and y1 are equal, but we see before that, which one's the red equation? Before that, y2 is greater than y1, and after y1 is greater than y2. All right, so what do we need to solve our inequality? Go back to the beginning of the problem. We're trying to figure out when y1 is less than or equal to y2. All right, then according to our table and our graph, but we'll look at the table because we're asked to solve numerically, we see that for all of these values, y1 is less than or equal to y2. Also, even though it's not shown in the table, if we kept scrolling up and getting more and more negative, we would still see that y1 is less than y2. Okay, so that gives us our solution. For all of the numbers, all the way until we get to x equals 2. So everything from x equals 2 and below will give us a solution. Is x equals 2 included in our solution? Yes, because we had a less than or equal to sign. Okay, so from the table, we can see that our solution set Oh, my devices are dying on me today. From the table, we can see that our solution set is everything less than 2. So our answer would be x is less than or equal to 2. And then an interval notation is written down below, but I'll write it here. That's negative infinity to 2 with the 2 included. So we put a bracket around it. So again, to solve numerically, we put one side of our inequality into our calculator as y1. I think my screen froze, as y1. And then we put the other side in as y2. And then we go to the table and scroll down to compare the outputs. When is y1 less than y2? When are they equal? When is y1 greater than y2? And then based on the inequality that you start with, you should be able to find your answer. All right, any questions about solving graphic or numerically? And even though it wasn't explicitly said here, because the graph is here too, we can see that it's pretty easy to solve this graphically as well. You would graph the two lines, find the intersection point, and then we see to the left of that, the red line is above the blue line, so y2 is bigger. And to the right of the intersection point, the blue line is above the red line, so y1 is bigger. So depending on what your inequality says, if we want to know when is y2 greater than y1, or when is y1 less than y2, that's the same question. That would be everything to the left of the intersection point, so negative infinity to 2. And then everything to the right of the intersection point, that's when y1 is greater than y2. So it's finding the intersection point and analyzing what's happening to the left and right of it. All right. We just do at least one example where we solve graphically and numerically on our own. So let's do this one. Problem number 2, because the graph's already here for us. It says solve each inequality graphically. So we're given two functions here. F of x is in the red, and g of x is in the black. And then we're asked to determine where, for the part A, where is f of x equal to g of x? So that's an equality or an equation. We can see from the table that f of x and g of x are equal at this point when x equals 2. So for these, we're trying to find the x values that work. Our solution for part A would be x equals 2. That's it. We're just finding the intersection point when they're equal to each other. We get more interesting solutions when we look at parts B and C. Part B is asking, what color should we use? Let's go pink. When is f of x greater than g of x? So f of x is the red line, g of x is the black line. When is the red line greater than the black line? We see that that's happening all over here. F of x is greater than g of x. What x values are covered? It looks like it's all of the x values that are less than 2. Because once we get to 2, they're equal. Okay, f of x is greater than g of x for all x values that are less than 2. That's it. It's just analyzing the graph. And then last one, I'm running out of colors. I guess I can do purple again. All right, when is g of x greater than or equal to f of x? So greater than or equal to f of x. One, we can see that the black line for g of x is above the red line for all of the x values bigger than 2. But this time we're also going to include the 2 because that's when g of x is equal to f of x. So our answer would be everything bigger than 2 and including 2. So our answer would be x is greater than or equal to 2. And just to be thorough, let's write these in interval notation as well. X is greater than or equal to 2 would be bracket 2 to infinity parentheses. X is less than 2 would be parentheses, negative infinity to 2. And x is equal to 2 doesn't have an interval notation. It's just one number. In section 3.4, we talk about something called compound inequalities, which is just basically two inequalities in one. So you're solving two inequalities at the same time. We're going to do a couple of examples of that, and then we're going to move on to talk about absolute value problems, which you have to use inequalities to solve. So let's look at one example from section 3.4 with our compound inequalities. And again, a compound inequality is an inequality joined by the words and or the words and or. And then you put the two, you're compounding two inequalities. So you're putting two inequalities together. The solution to a compound inequality is a set of all values that make the inequality true. So same as what we had before. We're solving two inequalities at one though. So and versus or. Okay. A compound inequality with the word and is putting two different inequalities together. So x is greater than, well, let me not say it that way. The solution has to satisfy both of these things. So we want x values that are greater than or equal to -5 and less than 2. So you have to satisfy both of these inequalities to be true. Okay. So let's look at that one visually on a number line to help us out. Ooh, my number line's a little wavy, but that's okay. So if -5 is down here and 2 is over here, and then 0 would be somewhere in there. All right. If I want all of the values that are greater than -5 or equal to, that'll be -5 all the way up to infinity. And then if I want all of the values that are less than +2, open circle around the +2 and then shade in, I don't want to cover it up, shade in everything less than -2. Since this is an and problem, our solution is going to be the set of numbers that are covered by both the pink and the green line. We need for the x values to satisfy both inequalities. So that would be everything from here, including the dot. Okay, putting these two together, our solution would be from -5, including -5, all the way up to 2, not including 2. Those are the points that are shared by both of those solutions. So for an and compound inequality, your solution has to satisfy both of the original inequalities that you're given, which is the opposite of an or inequality. So if we had x is greater than or equal to -5 or x is less than 2, then for an or inequality, we're looking for any x values that work for either one of those. So either the number is less or greater than -5 or equal to -5, or the number is less than 2. So looking at that again, I'll use the pink. It can't stick to my same colors. Let's see. So we had our -5, our 0, our 2. For the -5, we said, boom, that's this. So all of these numbers from -5 all the way to infinity have to be included in the solution because they satisfy the first part. And all of the numbers from -infinity to 2 would also be included in the solution. So we want everything that's covered by either the green line or the pink line, which, as we can see, the entire number line ends up being shaded. So every single number is either greater than -5 or less than 2. So our solution for this one would actually end up being all row numbers. Our solution is everything, which is -infinity to infinity. So and means that both things have to be satisfied, or means that either of the things have to be satisfied. All right, let's jump into some examples where we see problems like this. All of these are already done for us, so I want to jump to the practice ones. All right, here are two practice problems. Solve the following inequality, graph the solution, and write the solution set in interval notation. For part A, we have 5x minus 3 is less than 9, and 3x minus 4 is greater than or equal to 11. So this is an and inequality we're going to do a practice problem for. For the first part, 5x minus 3 is less than 9. And then for the second part, 3x minus 4 is greater than or equal to 11. We have to, oops, don't look at the solution. We have to solve both of these. For the first inequality, we'll get 5x is less than, what's that, 12. And then if we divide both sides by 5, x is less than 12 over 5. All right, let's keep that in mind. For the second one, we have 3x minus 4 is greater than or equal to 11. So 3x is greater than or equal to 15. And then dividing both sides by 3, x is greater than or equal to 5. So we want both of these things to be true. Let's look at our number line. We're going to graph both of these inequalities and see where they overlap. All right. Well, 12, let's see. Both of these are bigger than 0, so let's make it easy. 5 would be, we don't have to be exact. Here is 5. 12 over 5 would be smaller than that. So if 5 is here, 12 over 5 is a little bit bigger than 2. Okay. So 12 over 5 is here. All right, let's start with the 12 over 5 one. We want everything less than 12 over 5. Open circle, shade in everything less than. That's this. And then for the other one, we want everything greater than or equal to 5. And then you have to ask yourself, where do these two, the pink line and the green line, where do they overlap? Are there any numbers that are both less than 12/5 and greater than 5? No, no such number exists. So our solution would be no solution. So notice that the graphs do not share any common points. So there is no solution. Remember, for an and problem, you're looking for where the graphs overlap, okay? And there's no interval notation if there's no solution. There is no graph, so that's it. Nothing to do there. I should note, if this problem was exactly the same, except it was or instead of and, the solution would be everything covered in pink and everything covered in green. So you get both things as your solution. All right, I just want to do one problem that's an or problem, and then, or a compound one that's double, and then we'll stop. So many good ones. All right, we might have to revisit this in the next class, but that's okay. I'll draw up here. So this is a compound inequality where we have double inequalities and they're written together. If you have two expressions where both of your inequalities share a point, or share an expression, and the inequalities are facing the same direction, then we get something called a double inequality, and we can solve both of the inequalities at the same time. So we'll do let's do problem B, because it has a negative in it, a negative x value, and I'm excited. All right, so this is -5 is less than or equal to -5x minus 6, which is less than or equal to 3. So if you look at this, it's really two problems. -5 is less than or equal to -5x minus 6. And then the other one is -5 minus 6 is less than or equal to 3. But we can solve them both at the same time by trying to isolate the x in the middle, okay? So we're going to take the -5x minus 6 and try to get rid of the -5 and the minus 6. So we're going to start off by adding 6. And you have to add it in each of the three parts. So we're going to add a 6 to the -5, add a 6 in the middle, and add a 6 to the 3. This gives us 1 is less than or equal to negative 5x, which is less than or equal to 9. All right. So that's step 1. Now in the middle, we have a negative 5x. We're trying to get the x by itself, so we need to get rid of the negative 5. And do not forget, when we multiply or divide by a negative, that changes the direction of our inequality. So if we divide everything by negative 5, first let's look at the numbers. We get a negative 1/5, and then an x, and then a negative 9/5. But very, very important, instead of having less than or equal to signs, they now become greater than or equal to symbols because we divided by a negative. And we're actually done. That's our answer. So our solution set is all of the x values between negative 9/5 and negative 5/5. Okay, so solution, I'm going to write it in the other order because we want to start with the smallest number. Negative 9/5 is less than or equal to x, which is less than or equal to negative 1/5. So x is between those 2 points. We have less than or equal to signs, so we'll have brackets for our interval notation, and then both of our endpoints are included. Negative 9/5 to negative 1/5 would be our solution.